Good evening, everyone. So this week is the Students' Week. Here we have two speakers. So the first one is from IIT Kharagpur, Sayantan Pal, on nonlinear guidance for impact angle constraint target interception under field of view and input constraints. So he's a doctoral student at the Department of Aerospace Engineering, and it's all for you, Sayantan.
Thank you, sir. Thank you, sir. Thank you for nice introductions and for inviting me to present one of my work in this nice platform, Robotics Café. So, today's talk is on nonlinear guidance for impact angle constant target interception under FOV and input constraints. Let's begin with introduction. So, target interception plays a crucial role in modern defense applications such as precision strike, autonomous weapon systems, and missile interception. But traditionally, the guidance laws mainly focus on minimizing the miss distance. However, in many practical missions, simply hitting the target is not sufficient. The interceptor must hit the target with a desired orientation, which is also known as the impact angle constant. At the same time, the practical limitations also must be considered. So first, the target must always remain within the seeker's field of view limits. Otherwise, the interceptor may lose the target lock. Second, the interceptor cannot generate the unlimited accelerations because of the actual limitation. So therefore, our objective is to design a guidance law which will satisfy all the practical requirements simultaneously. Now, I am defining my problem formulations in a formal way. So, this is the schematic representation where aim is represented. This is a two planar interceptor target engagement geometry where aim is represented as the interceptor and P is represented as the target. And Vm and Vt is the velocity vectors of the interceptor and the target respectively. And Am is the lateral acceleration of the interceptor. Similarly, the gamma m and gamma t are the flight path angles of the interceptor and the target, and lambda here represents the LOS angle, and delta is the look angle. So two assumptions we have considered in this work. One is that the velocity of the interceptor should be larger than the velocity of the target, and initially the another assumption is initially the target should be inside the field maximum FOV limit. So after that, and in this work, our main objective is to we have to design a guidance law which will intercept the non-maneuvering moving targets while considering the impact angle, field of view, and the input constants in the guidance law design framework. These are the before designing the controller, we make use of two existing theoretical results. So the first lemma here actually provides the stability conditions for the systems with variable Lyapunov functions, and the second lemma is establishes the relationship between the relative velocity and the maximum field of view limit. But these two lemma which we will use in the further controller design section. So now the time is to design the guidance law. So here this is the planar engagement kinematics that is represented by r dot, lambda dot, and gamma m dot. As already I am said that we are designing the guidance law for the non-maneuvering moving target. So here we are considering that the gamma t dot equals to 0, and the components of the relative velocity, that is parallel and perpendicular to the LOS, are represented as VR and V lambda. First, we are introducing two variables, that is C1 and C2, with the help of maximum FOV limit, that is delta max. And using the assumption 1, we are finally come up with the range, that is C1 it should be less than 0 and C2 is comes with greater than 0. These two parameters we will use further in our design to consider the field of view constant into our design. Our main, this is one of our main contribution in this work, that is the introductions of a asymmetric smooth bounded function. So generally the existing guidance law employ the hyperbolic tangent function. In contrast, this function provides an asymmetric upper and lower bound and includes a tunable parameter A, which will control the smoothness of the function. So the two nice properties of this function is that is it is always remains bounded and it is positive definite. So in this plot, we are showing that the function effects with a varying of A So from 0.01 to 1, and so it is smooth, it is becoming very smoother when the A is increasing. So this function we will use in this controller design as a saturation function to consider the input saturation into the design. Another way also we have modified this function that is virtual controller. So here in practical systems, the interceptor acceleration is limited. So we should take care of it. So ignoring these limitations may produce the invisible control demand. So therefore, we are using this function. We are modified with the help of A max and A min to provide to show a asymmetric saturation model, which is represented by this. So, but in this throughout this work, we are considered that the magnitude of the A max and A min is same. But if some of the cases A max and A min is not same, then also this will work. So the main characteristics is it explicitly enforces the upper and lower acceleration limit, and there is no switching logic. No, it will avoid the discontinuities and switching logic. So now the time is to introduce this acceleration to input saturation into the interceptor kind of dynamics. So we have modified the gamma m dot from AM by VM to saturation of AM by VM. So which will guarantee the physical realizable guidance commands under input constraints. So now the time is to design the controller. First, we are defining the two tracking errors, that is E1 and E2, where E1 is the LOS angle error, lambda minus lambda f, and E2 is the relative velocity error, that is V lambda minus V lambda f. So from this function itself, we are proposing this V lambda f in this way, where CA1 and C2, we are defining that C1 plus sigma. C1 also previously we have defined, which is less than 0 and it is greater than 0 with the help of delta max. So these actually will use to consider the field of view constant, and according to the boundedness property of the function, the V lambda should be less than CA1 and it is and sorry, greater than CA1 and less than CA2. So, and the main theoretical results are summarized in this theorem. So, considering the engagement kinematics and the tracking errors E1 and E2, if we choose the lateral accelerations of the interceptor by this expression where A, B, and G2 and G2 are expressed in this way, and then another auxiliary variable chi, which will take care the input saturation compensation, and the dynamics is represented by this, then the tracking error converges to asymptotically, and the field of view constant is satisfied throughout the engagement, as well as input saturation is explicitly respected. So now for the proof of this theorem, we have used the Lyapunov framework, Lyapunov structure framework. So first we have defined the composite Lyapunov functions for, that is V1 plus V2 plus V3, where V1 is considered with respect to E1, that is the LOS angle error. So after differentiating, we have come up with these expressions for V2, which will take care of the field of view constants. Here we are using asymmetric integral radial Lyapunov functions. We are employed from these references. And according to this reference, this function has follows this inequality, and it holds for V lambda should be less than C1 to C2. And after simplifications, we are come up with this expression, while V lambda f already we have defined earlier based on this function. So now after differentiating V2, this expression is coming, and then we have to substitute this A, B, G2 and G2, which we have defined in here. And after simplifications, we have get finally this V2 dot equals to A plus B into E2 dot. So, and the rate of change of E2 dot is come in this way, and then substituting E2 dot in this expression, and finally V2 dot is. So then now the time is to substitute the aim, which we have to choose the aim in such a way that the terms will cancel out, and using the Young's inequality, we can get finally this expression. So till now we have considered this way the impact angle and as well as field of view. But to consider the input saturation into the guidance law design, we have considered another Lyapunov candidate, that is V3 half of chi square, and using the chi dynamics, finally we are getting this, come up with finally this expression chi into in bracket minus 1 by chi into chi plus delta m cos delta. So finally the total derivative, the composite derivative, the time derivative of composite Lyapunov function v dot equals to v1 dot plus v2 dot plus v3 dot, and substituting this v1 dot, v2 dot, v3 dot, we are finally come to this expression. So, and from as this function is a positive definite, and from the inequality property of that integral Lyapunov functions of these, and as this is the v3 now 1 by 10 chi square. So finally, we are able to come up with this expression. And according to lemma 1, where the stability conditions for the virial Lyapunov functions was given. So according to lemma 1, the composite Lyapunov function is bounded for or t greater than or equal to 0. So thus, the proposed guidance law guarantees the bounded tracking errors and respects the input saturation constraint as well as field of view constant take care throughout this guidance law design. So now I am showing the performance study of this guidance law. So these are the simulation parameters we have used, where the initial interceptor position is 0, and the target is showing as a t naught, that is 15,000, 0, and interceptor speed and target speed is represented by 350. And for initial right path angle of the interceptor, and sorry, it should be target, it is both is 30 degree I have considered, and maximum loop angle is 70 degree. And maximum lateral accelerations is 15 g. So I have considered AM max and AM is both plus minus 15 g. And these are the guidance law parameters. So in these simulations, we have used the kinematic model to intercept the non-maneuvering target interception. And we have considered the miss distance for all the simulations for r less than or equal to 0.1. So first here I am showing the interceptions with impact angle of minus 90 degree. So from this plot, this is the flight path angle plot, and from this plot, it is evident that the interceptor is strike the target with minus 90 degree, and it respects the maximum lateral acceleration of 15 g from this plot. And we have considered that delta max is 70 degree, and the look angle profiles confirms that it is within that, and this is the range profile. So from this simulation, this trajectory plot, it will show that the target interceptor will strike the target with 90 degree of impact angle. Here, with the different impact angles, we have verified this performance study of this guidance law from minus 30 degree to till minus 330 degree. So for all the case, the interceptor is perfectly hitting the target with the desired impact angle. Here also, for all the case, it is satisfying the lateral acceleration limits of plus 15g to minus 15g. And this is the flight path angle profile. And for all the 6 cases, it will show that the minus 30, this is minus 690, this is minus 150, and for all the cases, the impact angle is achieved. And 70 degree is the maximum look angle we have considered, and it is respected. This is the LOS angle profile, and this is the relative distance between the interceptor and the target. That is range. So these profile is shown here. We have analyzed the sensitivity analysis of A1. So this A1 is actually used in our input saturation model, where we have proposed based on this asymmetric function. So if we are varying here, the 60 degree impact angle cases we have considered. So we are varying the A1 from 1 to 80, and it is showing that as A1 is increasing, the smoothness of the lateral acceleration profile is also increasing. So when A is less, so it is quite steep. This is the steeper profile. And for all the cases, the interceptor is strike the target with the desired impact angle and maintaining the field of view limit also. So this is one sensitivity analysis of A1. Another sensitivity analysis we have done with the A2, where the virtual guidance law, virtual controller also we have proposed based on our asymmetric smooth bounded function. So based on the function, the A2 was there as a positive tunable parameter. So there also, if we are, this A2 actually regulates the lateral accelerations profile. So it has a effect on the total control effort. So if the A2 is more, the lateral acceleration is quite less. So it reduces the control effort. And when the A2 is less, the lateral acceleration requirement is more. So the control effort is also increased. But see, for all the cases, the interceptor hit the target with the desired impact angle of minus 60 degree, and it respects the 70 degree of delta max, and 15 g of maximum lateral accelerations profile maintained here. So this work is first these guidance law is based on the non-maneuvering moving target, but for a small maneuvering target, in this case I have considered the lateral accelerations of the target as a 1 meter per second square. So for that also this guidance law, for a slow maneuvering target, this guidance law can work. Not for the high, and if the acceleration is unknown, for the target acceleration unknown, then we have to use some additional adaptive guidance law. So that will work further. But for slow maneuvering target also this guidance law can work. So here I have considered the minus 150 degree of impact angle, and this is the same, the 15g, and the delta max is 70 degree we have considered, and the interceptor is perfectly strike the target with the desired impact angle while maintaining the field of view as well as lateral acceleration limits. So for these, exactly for the same cases, for 6 different impact angle cases, I am verified for the maneuvering target also. So the interceptor is perfectly strike the target with the desired impact angle, and it will also respect the lateral acceleration limits as well as field of view limits. This is the LOS angle profile, this is the range profile. So now the time is to comparisons with the existing guidance law. Here the comparison matrix we have considered as the total control effort, which is calculated as the integrations of 0 to TF, where TF is the interception time of the lateral acceleration square dt. So we have considered 7 different impact angles for these comparisons. So these and 3 existing guidance law where they have used in their guidance law design that hyperbolic tangent function. So that is why we have chosen these 3 papers. So for these 7 different impact angles, we have got that the proposed guidance law requires a less control effort, and for these 3 guidance law, this is guidance law, the guidance parameters are considered same as the references what they have given in their paper. And one case of simulations we have shown here, and that is for the minus 60 degree of impact angle, where blue one is my proposed guidance, and the red, the magenta, and the green one is Liu, Joe et al. And Dan et al. And for all the cases, all the guidance law perfectly strike the target with the desired impact angle of minus 60 degree, and all the guidance law respect field of view limit. And but those 3 guidance law have not considered the input saturation into their guidance law design framework. But at the time of simulation, they have used it as a Hertz saturation. So I am using that only as a 15G. And from that zoom plot, it's clearly shown that our proposed guidance law is smooth. There is no such discontinuity in that portion. And this is the lateral acceleration profile, and this is the LOS angle profile, and this is the range profile. So from the trajectory plot also, it is showing that all the guidance law perfectly strike the target with the desired impact angle of minus 60 degree. So here now to conclude, here I have proposed an asymmetric integral variable Lyapunov function-based guidance law for intercepting the non-maneuvering targets with desired impact angles. Here we have introduced a asymmetric smooth bounded function, which we will use in our input saturation modeling as well as virtual controller design. And here in this work, we have considered the field of view as well as input saturations to make it practically applicable. And we demonstrate the superiority of this guidance law of the compared to the existing guidance in terms of reduced total control effort. And our future directions will be extension to this 3-dimensional engagement scenario, this guidance law, as well as considering maneuvering targets where the accelerations of the target will be unknown, and for a high maneuvering target also that will work. So these are the references. Thank you, sir. Thank you all. And now I'll be happy to answer any questions.
Thank you, Pal. Nice talk. Any questions?
Hi, Sayantan. Yeah, so I have a question in this particular slide. If I can see, the acceleration demand towards the terminal phase is very high. How about if your interceptor does not
Yes.
have that kind of uh, fuel or that kind of facility that it can take a large turn and hit the target? Then it will be missed, right?
Yes. So actually, for the higher impact angles,
No,
if
I'm not
you will
asking
see
about
that
higher.
these
I'm not asking about higher impact angle. I'm just asking that your interceptor is taking a. If you see the AM plot, your
Huh?
interceptor is taking
Huh?
is asking a huge acceleration at that particular terminal phase. So if the interceptor does not have
Yeah,
that kind of acceleration at that time, then it won't be able to hit, right?
so that then we have to, based on this interceptor only, we will give the maximum lateral acceleration, that is A max. Here I am considering 15. So maybe on that time it has a less actuator capability, maybe 10. Then on that time also it will work based on that. Maybe on that time it will be saturated. Exactly, it will start from the 10 and it will be saturated on 10 and intercept the target. But based on that, we have to give the maximum acceleration limits.
Uh, okay.
Are you getting my point? Actually, I just want to say that these maximum acceleration limits is in our hand. So that is one design, that is one parameters for the simulation I have used here, 15. So if the interceptor has not capable to with this 15G, maybe 5G, then we have to design our guidance with 5G of acceleration limits. Then also it will
Okay, so
impact.
you are saying that towards the terminal
Hmm.
phase, if the interceptor has
Hmm.
5G limit, then you will
Hmm. Then
design
also it will
with a
intercept.
5G limit, right? Okay,
Yes,
okay,
yes, yes, yes.
okay, okay. Thank you.
Hmm. Thank you. Thank you.
So Shantan, I have a quick question. So have you
Yes, sir.
thought of combining these like model-based guidance with some kind of learning-based, like with more recent techniques and looking at like because why I'm saying learning-based is because there's a lot of dynamicity that is involved where your
Yes.
target can change direction or things like that. Like so, any work you have looked into that space or
Yes, 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 yes,
ways to
sir. In
combine?
recent
How can
literatures
you
also,
combine this? Yeah.
that I will think of it. Even I will work on it also for maneuvering target. Maybe we will come up with that things only, because for a classical based controls what we have designed, then for adaptive law we have to design, and for a unknown maneuvering target it can work. But in a very recent literatures, I have found that there are some learning based and data driven control is also there, which will work in this area. So that we will look for. Now I am not working on that, but maybe I will work on it.
Thank you.
Thank you.
Astha, we can go for the. I think we'll take this as last question and then we'll move to the next talk. Yeah, Astha, you can go ahead.
Hi, sir. My question was ki, since so I was thinking ki you're doing it for non-maneuvering targets, but if your vision sensors are good enough to estimate the velocity of the target, you can perform the same thing iteratively for a maneuvering
Yes.
target. So what could, if the vision side is sorted, then can we do that? Can you proceed with
They then also, for again, for slow maneuvering target, this guidance law can work. But for if the maneuvering target is quite high, maneuverability of the target is quite high, then
Mhm.
we have not proven that this guidance law will work. Okay, maybe for that we have to design the guidance law by considering the AT, maybe the accelerations of the target into our guidance law design formulations. Then for any such target maneuverability also, this guidance law will work. But till now, we can say for a slow maneuverable target, this guidance law can work.
Mhm. So I think then we can conclude that slow maneuvering target means that vision sensors take more time to give you the
Yes, yes, yes.
velocity of the target, and if we increase the velocity estimation, we can also do this for high, matlab, faster maneuvering targets.
Yes, yes, I think we can. But it is
Okay,
not proven till now. We have to do this work.
got it, sir. Okay,
Yeah.
thank you, sir.
Thank you.
Okay, thanks, Shantan. I think we'll end the Q&A session now here for this talk, and we'll introduce the next talk. And thanks
Okay,
again.
thank
Let's
you.
thank Shantan once again for his time and enthusiasm
Thank
and
you, sir. Thank you.
sharing his work.
Thank you.
Yeah, I think other like if people have questions, they can reach out to you. I hope.
Yes, yes, yes. Sure.
Yeah, sure.
Thank you.
Okay.